Okay, we're probably going to get started. So anybody who comes in a bit, hopefully you can check out the slides online or you can talk to me after. So my name is Daniel Roesler. I'm the co-founder and CTO of a company called UtilityAPI. We automate the process of interacting with utilities. So we're used by a lot of solar companies and energy efficiency companies. And I say all that because I want to emphasize, and my big disclaimer is, I'm not a professional security analyst. I do this sort of thing for fun. I'm a big privacy advocate. And so I do a lot of crypto side projects. But my normal day job is something completely different. So take what I say with a grain of salt. And if you are a security expert, then please come up afterwards and tell me what I got wrong and why this presentation sucks or whatever it is that you want to tell me. So, okay, so how many people here have heard of WebCryptoAPI? Okay. How many people know cryptographic principles like symmetric encryption and asymmetric encryption and cryptographic signing? And okay, how many people have never used crypto before? Okay, this is probably not the stuff you want to use. So WebCryptoAPI is a standard that allows access to cryptographic primitives in the browser. And so this is pretty low-level stuff. It's not necessarily something you want to use by itself in your web applications, but there are several frameworks that use these primitives in the base layer. The idea is that you want the browser to offer the constant time implementations of these cryptographic primitives so that you can sign, you can hash, you can verify, you can encrypt, etc. Oh yeah, can everybody hear me? Yes? Okay. So you can use these in your web applications, but generally you want to have a good understanding of what the different types of encryption and signing and cryptography that there is. This is the link down here. Hopefully it's kind of unfortunately pretty low, but this is the W3 consortium standard that they're working on. It's implemented in Chrome, Firefox, Safari, so it's available on mobile. It's partially implemented because the standard contains things that browsers have refused to implement, which is hilarious, but that's the way crypto goes sometimes. It also does not contain some of the latest awesome stuff, and all these slides are available online afterwards. Okay, so let's get into the meat. This is actually the actual API overview. So we're going to dig into actually what is available in the API itself. So it's under the window.crypto module. And if you'll notice, the only thing that's available under the base level module is get random values. So that's a random number generator. It is cryptographically secure, so you can generate cryptographic keys and random bits of data based on this. You don't have to use math.random anymore, thank God. So this is kind of the best replacement for that, and that is available on pretty much every browser that's up to date. I think it's even available in IE 10 or 9. It's definitely available in 11. So the next thing, it gets into the subtle. So the subtle gets down into the actual primitives themselves. So there's a whole bunch of different functions you can do on the subtle module. The first is key handling. There's a bunch of assorted functions for key handling. Generate key, import key, both return what's called crypto keys. And crypto keys is a specific object for this API. And export key will allow you to export those keys to something that you can transport or something you can give to a user or something you can base64 encode. So this is the way that you get keys out of the system. Wrap key and unwrap key are functions that allow you to encrypt other crypto keys for storage. So if you have, generally, if you generate a public-private key pair and you want to save it to something like local storage, you will, you generally want to wrap that in a password-based key that I'll get into later. So that's a good technique for storing generated keys safely in either local storage or exporting them, etc. And then derived key and derived bits are available to, and you can't actually, yeah, you can't see it down there. Oh no, it's cut off at the bottom. There's actually derived bits down there that's used for generating keys from handshakes or key exchanges, so like Diffie-Hellman or elliptic curve Diffie-Hellman, etc. Change my resolution? Okay, let me try this. Ah. I think it's, yeah, it's just cut off at the bottom. Try that. Okay, awesome. Here we go. That'll do. Okay, the next one is you can sign. This gets into the meat of what you can do with those keys. So you can sign and verify data, and that's really easy to remember. It's just sign and verify. And you can encrypt and decrypt data. That's also really easy. And then you can hash data. So that's things like SHA-256, etc. So cryptographic hashing. Anybody have any questions so far? Please stop me. I'm actually going to get into more. This is probably going to be the most boring presentation you'll see all day. Yeah? Yeah. Yes. So I'll go over what browsers implement what, and I also have a test table that you can open up in a browser, and it'll tell you what parts of the standard are available and what aren't. So, okay. So to start off, random number generation. So it's pretty easy. You pass it array buffer, or well, a typed array, and it will return a typed array of the same length of that same type filled with random numbers. It's pretty straightforward. It's actually really awesome. So I would highly recommend using this. I pretty much use this exclusively. I rarely ever use math.random unless I'm doing some sort of, I don't know, pretty visualization that I need some random data for. But this is something you should use for pretty much every sort of UUID that you want to create, or key generation, or anything where you need a set of truly random number. Not truly random, but cryptographically secure. Okay, so generating keys. First, you pass the name of the algorithm. So in this case, it's AES-GCM, and then there's other sorted parameters you can do on top of that. You can set whether or not you want that key to be extractable, whether or not you can export it. So if you set that to false, which you can actually say to the browser that never let this key leave the implementation of the browser. And so that allows you to basically keep the key safe inside the browser without having any sort of other malicious JavaScript have access to it. Now, if you have third-party code or third-party JavaScript libraries or whatever. And then the usage settings are the arrays that you can, array of usages that you want that key that you generated to be able to do. And so that's limited based on the type of key that you generate, and I'll go through that a little bit later on. Yeah? Yes? Exactly. So the browser is in charge of handling the keys when they're in crypto. The only way that you can get access to the raw, say, modulus or bits of key data is via the export key function. All right, import key. So that's if you have a key from outside the browser or you saved it previously. So this is an import key function. You specify the the name of the format that's incoming. So the most common in web crypto is JSON Web Tokens, and so that's actually an object, and it has like things like the algorithm, the number of bits, and the actual key data that's base64 encoded. The raw data itself, so that is the key that is incoming, the algorithm that you want that key to be, and so this is basically kind of a copy if it's a JSON Web Token. Whether or not you want the key to be extractable and how you want the key to be used. So pretty similar to the generate key. Export key is how you get keys out. So if you have a crypto key that's you've generated or something like that where you set it extractable to true, you can specify the format and the key itself, and it will dump it to whatever format you have. So there's a big old long list of what types of crypto keys can be dumped to what types of formats, and I'll go through that later as well. Okay? All right, one of the things that I should probably note that I guess I forgot to note earlier is none of these things are synchronous. They're all promise driven. So this actually returns a promise, which you can do a .then and .error afterwards. So this is kind of what this API uses is the promise specification. The only thing that's synchronous is get random values. Okay, wrap key is you taking another crypto key and wrapping it with a synchronous symmetric key. So you specify the format that you want to dump the key into. You specify the key itself that you want to wrap. You specify the wrapping key, which you've generated previously. And you specify the format of that wrapping key itself. So that's basically used to export a key to storage. So if you generate a ECDSA key, and how many people know what ECDSA is? Okay, so it's one of the algorithms that's available in the API, and this allows you to safely store generated keys with a password. And I'll go how to generate a password with this. Yeah. Or sorry.
Wrap key differ from encryption?
Yes. So wrap key is basically a more specified type of encryption. It is encryption, but you can only encrypt crypto keys. So basically, since you don't know the crypto key itself, so if you specified some sort of key that's extractable, but it's held in memory, you never have to really see the bits of data yourself. It'll just create those crypto key objects for you and wrap them and store them for you. So I think it's kind of silly and a little bit overextended part of the spec, but it's available, and I figured I should cover it since this is basically an overview. So unwrap key is basically the reverse. You specify the format that you dumped it to, the wrapped key itself. So that was what was returned by the promise in the wrap key function. The wrapping key is the key that you basically wrapped it with. This is the wrapping algorithm. This is the wrapped key algorithm, which was the format of the key that you had wrapped, and whether or not it's extractable and the usages. Okay, derive key. This is a little bit more fun. So when you do a Diffie-Hellman key exchange, you basically give somebody else some public key, and then they combine it with their private key, and you now have a shared secret between them. So when you have an ECDH, which stands for elliptic curve Diffie-Hellman, when you generate those keys, you have a private crypto key and a public crypto key. And you can export that public crypto key and give it to somebody through some sort of exchange, and they combine it with their private key in order to form a secret key, and that's what this function does. So if you get a public key from somebody and you combine and you generate your own ECDH key pair, you can combine that private key with that public key and create a shared secret, so like an AES, which is a symmetric algorithm. And then you can specify whether or not that key is extractable or whatever. So this is good for creating shared secrets between two people without either one of you having access to each other's private key. So you can do this key exchange in a public forum, which is really awesome. That's what I love about asymmetric crypto. Drive bits is basically the same thing, only you don't create a key. You just specify some length of bits that you want. And so if you have some sort of other AES algorithm or something like that that you want to use, you can do this as well if you want to export that data. So this is used to create symmetric keys from asymmetric or password-based key derivation functions. So it can be used with password-based key derivation functions. So how many people PBKDF2? Okay. Okay, that's part of the standard. Basically what you can do is you can specify in this, instead of ECDH, you say this is PBKDF2 and specify the number of rounds and the type of hashing. And the base key is basically your password input, so a string or an array of data. And then it will hash it that many number of times safely and generate a length of bits from that. And so that's how you can create the wrapping key from a password safely. So it's basically a derived way or a predictable way of generating a set of key data that would be hard to reproduce because you have to go through that many rounds, like 10,000 or 100,000 rounds of hashing. So, and I think you can specify a salt in there as well, which is awesome. Okay? All right, so that's the key handling. That's how you generate keys and handle keys and export them and transport them and store them safely. So for signatures, you take the, if you want to sign a piece of data, you just take the algorithm that you want to sign. So it can either be asymmetric or symmetric. So in this case, it's an ECDSA, which is an asymmetric algorithm. And you take your signing key, so in this case, a private ECDSA key, and the data you want to sign, and you get back the signature itself for that data. If you want to verify, you say this is a asymmetric verification. You say this is the public key that I have. This is the signature that I got, and this is the data that it should have, and it will return whether or not that signature is verified, so basically true, false. Encryption. So whenever you want to encrypt some data, you use the encrypt API, and you specify the algorithm, and then the key itself. So what you want to, and then an array buffer of the data that you want to encrypt. When you want to decrypt, you use the decrypt function. And so all of these functions are linked. If you want to look at this later, it'll actually take you directly to the specific part of the standard API docs, so you can read through them and see what's what. Unfortunately, I find the docs to be pretty lacking in examples of how to use these, so I actually wrote my own, which I'll go over at the end. Decrypt. You specify the algorithm, the key, and the encrypted data, and it'll return the decrypted data. So it's an array buffer, so you can specify images, whatever sort of file format you want. It doesn't have to be string-based. So this is all based on the typed arrays API that are available in most modern browsers. Well, I guess all modern browsers. Hashing. So SHA-256. MD5 is not available, so don't use it. SHA-1 is available, but it's discouraged. SHA-256 and up is encouraged. At least SHA-256 for any new stuff. You specify what type of digest you want and the data that you want to digest, and you'll get back an array buffer of the data that is hashed. And so you can convert that to whatever sort of either hex or basic C4 encoded or whatever, but you'll get back the array buffer. All right, algorithms. I don't expect you to read this, but this is the image from the standard itself. It gives little checkboxes around which algorithm can use which type or which function on the API. So for example, RSA can sign and verify data, and then another form of RSA can encrypt and decrypt data. So a lot of these, unfortunately, should not be used. They are only there for backwards compatibility reasons. So you really shouldn't have to worry about a lot of these. I'm going to tell you which ones you should worry about. So a lot of these are really, really bad to use and unsafe to use. So for the only reason that you should really use a lot of these algorithms is to deal with data that is already encrypted or you're trying to deal with. So things like open PGP messages or that sort of thing. Okay? All right, can everybody see the green and the red a little bit? Okay, so the stuff in the green is stuff that I would be okay with you using. The stuff in the red is stuff you should probably avoid using and only use if you absolutely have to. And the stuff that's crossed out isn't even implemented in browsers, and there's no plans to implement it whatsoever, so give up all hope. So to start off with, if you want to sign and verify data, you should probably use ECDSA, which is an asymmetric signature and verification algorithm, or HMAC, which is a symmetric signature and verification algorithm. So the difference between those is ECDSA will allow you to give somebody your public key, and they can verify signatures that you are a part of or that you have signed without having access to your private key. And HMAC is a signature that allows you where both parties have the same key. So they've done some sort of out-of-band key exchange or some sort of key derivation or key exchange. Okay? Encryption and decryption. AES GCM is really the only one that's a part of the standard that I would recommend. The rest are not authenticated, and so they're really, really risky to use. You would have to combine them and combine any of the other encryption stuff with some sort of HMAC or some sort of signature. So AES GCM is the only one that has any sort of integrity attached to it. So you should use that one. And if you need to do encryption via public key exchange, you should do a Diffie-Hellman exchange to derive an AES GCM key. So you should not, there's RSA OAEP, which I have, does anybody know what that stands for? OAEP? Okay, all right. So that's a asymmetric encryption standard, but there's a lot of padding issues. It's a limited number of space that you can encrypt with. So in general, whenever you want to do some sort of asymmetric encryption, you want to do a Diffie-Hellman exchange, elliptic curve Diffie-Hellman. You don't want to do a real Diffie-Hellman. You want to do an elliptic curve Diffie-Hellman to derive the bits of the symmetric key that you want to do. So for digest, 256 and up, don't use SHA-1. SHA-1 is being deprecated in browsers already, and I think it's like $100,000 is the limit. No, I think it's like $10 million to find a collision of your choice in SHA-1, so it's not that expensive. Derive key, derive bits. So that's elliptic curve Diffie-Hellman. Diffie-Hellman, I think, is partially implemented by Firefox, but not by Chrome, and there's no plans to do it in Chrome, so don't worry about it. Password-based key derivation function 2 is what you use to convert passwords into bits. There's other better algorithms, scrypt and bcrypt. And those are not, unfortunately, part of this standard, but they could be added in the future, and in which case I would turn that one to red and say use script. Wrap, unwrap keys. So AES GCM, again, is a good option for this. There's also another algorithm called AES KeyW, or KW, stands for key wrapping. So that's another option as well. The main reason why you would use KW over GCM is because both of them are authenticated, I believe. And the reason why you use KW over GCM, and you probably won't, is KW doesn't require a random number generator for each individual encrypt. So GCM requires an initialization vector, which you should randomly generate every single time. But since you have get random values, you have access to random numbers. So just generate a new initialization vector every time. So, all right. Examples. So this is my repo that I have available on GitHub. It's my username, die5g/Webcrypto Examples. And basically what it is it's a gigantic list of all of the different algorithms and all of the different use cases that you could do. So SHA-256, see if can I increase here we go. Okay, so I say Webcrypto, subtle, digest, SHA-256, and then I want to hash 1234, and that will give me the hash of that data. So if I actually copy that, come on, there we go, and paste it into browser, I'll get back a nice little hash array buffer of the data as hashed. And so this would be compatible with OpenSSL or whatever sort of stuff you have. And it's something that is implemented in the browser. You don't have to roll your own crypto library or use a crypto library that's implemented in JavaScript, which is super awesome. Yay, finally. OK, so so you're welcome to browse all this. It's, of course, available. And you can copy and paste most stuff into your console to see how it works. All right. Come on. Go back. OK. So browser test. I also wrote a browser test where you can actually see what is implemented in the browser. Every check or X on this screen is actually a test to see whether or not that standard is implemented. So it basically copies that table that I showed you earlier from the standard and implements little scripts to see whether or not it's implemented. So for example, and this is Firefox. So you can see ASGCM is implemented, blah, blah, blah. All of these other ones that are backwards compatible, but AES CFB is not, and there's no hope. They don't plan on implementing it. So you can get a quick reference to see. You can also, I have it in Chrome as well. So you can see what's available in Chrome and Safari or whatever. OK? Questions? Yeah?
Do you have any indication as to why the API is wrapped in promise? Have you done perf testing on it? Seemingly, in an innocuous library to wrap in a promise.
I honestly couldn't tell you. It's been like that pretty much since the beginning. I think IE11 implements a version of this that is event-driven. And so you can say on complete or on error, that sort of thing, sort of like how Ajax is implemented. But they moved away from that after IE released that version and moved into promises. I have no idea why, but that's unfortunately the way it kind of goes. So a lot of these are really promise-driven. The reason why it's not synchronous is because a lot of this stuff takes a constant amount of time. So signature verification or decryption, et cetera, takes a constant amount of time, and that's the way it's implemented in the crypto libraries in the browsers. So I think Firefox uses NSS as its crypto library, and Chrome uses boring SSL as its crypto library. And so those have a specific implementation of these, and it would be hard to do it synchronously because your browser would freeze a lot. So for example, these RSA generation stuff. So if I want to generate this, look how long this takes. Yeah. So that's to do that synchronously would be really, really hard. So, I mean, they could have done a callback system or something like that, but I don't know, promises are sexy, I guess.
Yeah, that's where JavaScript is sort of moving.
Yeah, exactly.
So that's kind of an indication of what the performance is too.
Yeah.
Do you have any recommendations as to specific algorithms? Well, I guess that would align
Yeah.
very well with the efficiency of the algorithm.
Yeah, exactly. So the green ones are the ones that I would recommend. Of course, again, I'm not a security expert. I do this sort of stuff for fun. And so any security experts in the room, please stand up and tell me that this is not right, because I would love to fix it, or I would love a pull request. So looking for feedback, definitely. So ECDSA, which is the elliptic curve. So in general, the elliptic curves are a lot faster on generating keys because you just pick a point on the curve. You don't have to go through and find primes. And so that's a lot better. So ECDSA and ECDH, so elliptic curve, Diffie-Hellman, are the things you should probably be using for asymmetric crypto. For symmetric crypto, you just generate some random bits from get random values, and you're set for your key. So the only reason why you should be using password-based key derivation function is if you are using key wrapping. So you shouldn't be using password-based key derivation function for encryption keys themselves. Generally, you want to generate a random crypto key, like for an AES GCM key, and then you want to encrypt the data with that, because if you ever want to change your password, all you have to do is change the wrapping key itself. So basically extract the crypto key, generate a new wrapping key, and wrap it and save it again. So you want to only use password-based key derivation functions for wrapping keys. Yeah? Sure. So AES is really fast. So if you have an app and you want to store some data, say, on Dropbox for that app, right? So you can save some sort of AES or generate a public key let me start over. Okay. Say you want to, I don't know, save some sort of data, like a diary entry, to Dropbox via their web API, okay? You don't want Dropbox to be able to read that data. So what you do is you generate a private key, so that's AES symmetric key. You wrap that in some sort of password. So you use password-based key derivation function to generate a wrapping key. You wrap that. You save it to local storage, or you print it out and say, hey, user, save this file to your local computer. Then you use that AES key, the AES GCM key, to encrypt the data and then send it to Dropbox. Save it on Dropbox. So Dropbox never has access to the encryption key for that. And when the user loads the page back up, that key is either in local storage or whatever, and you ask for their password, you unwrap the key, and then you take that unwrapped key and decrypt the data from Dropbox. And so you can basically, this allows you to implement apps that allow you to store things on servers you don't control. Animating engines? So this is all client side. And so you wouldn't want to use any of this sort of standard with server-side applications. Node.js already has its own crypto library that implements a lot of more stuff than this. This is just strictly client-side, and so the only time you ever really want to use this sort of API is if you want to do client-side crypto, or you want to do some sort of processing on the client side. So stuff that is blatantly missing is a lot of stuff from libsodium, which is a lot more advanced elliptic curve cryptography that's a little bit better and a little bit safer. There is a little bit more speedy implementation of symmetric crypto. So it's actually a standard that's not AES, it's called Cha-Cha. And that is a little bit faster, especially on mobile devices. So this standard is relatively extensible. Since you don't have the actual algorithms as the API endpoints, you have the encrypt, decrypt, sign, verify, generate key, etc. as the endpoints, and you pass parameters to it of the algorithms you want it to use. It's pretty easy for browsers to add additional algorithms as they go on. So I think things like Curve 25519 and Poly 1305, etc. will be added, hopefully, in the future as this standards body goes through. So things that will never be added are AES CFB, AES CMAC, Diffie-Hellman, Concat. I don't even know what that is. Does anybody? No? Okay. And HKDF, which is another key derivation function. So I don't know why those are in there. I would love for somebody to tell me why those were in there in the first place. So, okay, I think that's what I have for this. Yeah, I can open it up for questions. As a reminder, when you're making web apps, you generally want to rely on a framework that implements this below it. You don't necessarily want to use these directly. So openpgp.js or Stanford JavaScript crypto library, all of those sort of things. I think Stanford is in the process of re-implementing their crypto library using these primitives when available. But I know openpgp.js does. I have my own library called Bring Your Own File System, which also encrypts stuff using these primitives and only these primitives, so you can't actually use it unless you have a modern browser that has this API available. So yeah, that's so one of the big things, not using it directly, because a lot of these algorithms, it's really, really easy for you to shoot yourself in the foot with these. I mean, look, there's very few of these algorithms on this screen that are green, right? And so if you're using this API directly, it's really, really easy to screw up and use another one or use an initialization vector twice. Because if you ever use an initialization vector for a different signature with this, somebody can derive your private key. So there's a lot of consequences that are really subtle, which is why it's in the subtle module. So there's a lot of things where you can shoot yourself in the foot with this library, which is actually why I've read a lot of security experts who are very opposed to implementing these sort of primitives in the browser and not implementing like basically a wrapper around them that says, it doesn't matter what algorithm it is, we'll decide that for you. Just encrypt some data. And you get back a blob. And then that blob has things like authentication, it has signatures, it has all the sort of thing that you really need to do. And so that's what the libsodium does, is it has secret box and just box, which are public and symmetric encryption. And it says, don't worry about what algorithm we use, we'll handle it, which is a lot safer. So I really look forward to when they make subtle go away and then they just add at the top level, get random values, encrypt, decrypt, sign, verify, and you don't worry about what algorithms they are anymore. The main reason why you're implementing the Subtle library right now, or the Subtle API, is so that people can use it with backwards compatible apps. If they had rolled their own SHA-256 in JavaScript, or were using one of the JavaScript-based ones, then they could just still use it to verify. Yeah? Okay. Yes?
Trying to get your data into a form that's hashable.
Yeah.
Care about cryptographic security. Would you recommend using any of these specifically for speed, or would you rather go into some browser implemented hashable?
In general, these will usually be faster. So the question was, if we are not focusing on cryptographic hashing, but just hashing in general, it doesn't necessarily have to be cryptographically secure. Is it better to use these implementations, or maybe something in like XXHash, I guess, in JavaScript? I would be very surprised, since these are APIs directly to the C implementation of the actual crypto library. I would be very surprised, unless your XXHash is actually in like asm.js or something like that. I'd be very surprised if they beat these on speed, even though these are built to be slower. So SHA-256 in this library is probably going to be faster, although I would love to be proven wrong. Probably going to be faster than XXHash in JavaScript directly, primarily because there's not any sort of garbage collection overhead or anything like that. Yeah. All right. We finished 2 minutes early. Fantastic. Oh, wait, one more. Sure. Yeah. So obviously, one of the most common ones that's used now is this digest. So digest is really used for seeing whether or not you've seen something before. And so if you're saving a piece of data to like images to local storage or to Dropbox or something like that, you can actually just hash it and store that as the file name, and then look up whether or not that hash exists. And if it does exist, you know you've already stored that file. And so it's a really easy way for determining whether or not something is existing or not existing in your local storage, that sort of thing, rather than having to scan all of the files and read the entire thing. So digest is a pretty good way for doing that. The rest of it is mostly for safely storing data on third-party servers. So like I said before, if you have a diary entry that you want to store on a third-party service like Dropbox or Google Drive, you can use this to encapsulate it with encryption beforehand. And then the third reason is end-to-end encryption for things like messaging or communication. So if you and another party are chatting and you want to do some sort of chat directly browser to browser or through a service without that service knowing what you're chatting about, that's a reason to use this as well. Now, there's a lot of reasons why you wouldn't want to use this, but the primary reasons are mostly storage. Yeah? OK. All right. Well, thank you very much. I appreciate it. Again, all the slides are online on daylightpirates.org or on my GitHub as well.